So today we're going to cover Chapter 7, Section 1. Today we are going to learn about angles of polygons. So the first thing we need to do is define or understand the different parts of the polygon. Now technically we've already seen all of these parts in triangles, but these same parts that we've seen in a triangle can now apply to any polygon. So just like triangles have 3 vertices, same thing for the polygons. So the vertices are going to be the common endpoints of 2 sides. The sides of the polygons are going to be the segments that form the polygon, and then a segment that connects any 2 non-consecutive vertices will be called a diagonal. Now in the particular picture here, the word vertex is right next to the C, but technically A, B, C, D, and E are all the vertices. And then the sides could be AB, BC, CD, ED, and AE. And again, when you name the sides, just like with the triangles, it doesn't matter the order. So when you go to name side AB, you could also call it BA. As far as the diagonals go, notice the definition there says 2 non-consecutive vertices. That means 2 vertices that aren't right next to each other. So for example, notice how they drew in the diagonal and it went from B to D or D to B. I could draw in another diagonal and draw it from D to A because A and D are not right next to each other. I can't draw a diagonal from D to E because that's a side. So that's what it means to be consecutive when it's right next to it. Now every vertice, I can have a whole bunch of diagonals going on here. So I could also draw diagonals out of E. I could draw a diagonal from E to B, E to C. So I'm not going to expect you to draw in diagonals. It will get kind of like spider web looking if your polygon is rather large. But just know where a diagonal is located because we're going to need to draw in the diagonals once we start with the parallelograms. So this slide has the names of the polygons. So you can name a polygon based on the number of sides that the polygon has. You should know and memorize these polygon names because if I give you a question on the quiz and I say how many sides are in a nonagon, you need to know that it has 9 sides. So the common or general name for the 3-sided polygon is triangle. 4 sides is a quadrilateral. Now this is what we're really going to be focusing on in Chapter 7 are the quadrilaterals and the specific quadrilaterals. Parallelograms, squares, rectangles, rhombuses, trapezoids, and kites. The 5-sided polygon is the pentagon. A 6 is a hexagon. And the way I remember 6-sided polygon is 6 has an X and so does the word hexagon. Because the next polygon right after that, the 7-sided also starts with H. So that's what helps me to keep tell the difference between the 2 H words. Then an 8-sided polygon is an octagon. I remember that because of an octopus has 8 arms. For the nonagon, if you think about the word 9, if you spell it, it sort of looks like it's trying to spell 9. But instead of an I, it puts an O. 10 sides is a decagon. I think of that as a decade, which is 10 years. Dodecagon is a 12-sided figure. And then notice it didn't list one for 11. There is a name for it, but you're not responsible for memorizing it. And then any side larger than 12, you would just write the number. So for example, a 50-sided figure, and then put dash GON. So anything 11 or then 13 or bigger, that's how you would represent the name for that type of polygon. So here, this is how they're developing the formula to find the sum of the interior angles of any polygon. So to find the sum of the interior angle measures of a convex polygon, you're going to draw all the possible diagonals from one vertex of the polygon. This is going to create some triangles. And if you remember, that the sum of the measures of a triangle is 180. So then you would just take 180 and then times it by however many triangles you create. However, you're not going to need to draw in the diagonals and figure out how many triangles it forms. I'm going to show you a formula on the next slide. Now, if you notice the first figure there, the triangle, notice that there are no ways to draw in a diagonal, because if I go from this vertice to draw to another vertice, it's the consecutive vertice. So there are no diagonals for the triangle, so this would be a sum of just 180 because it's one triangle. But if you have a quadrilateral, you choose one vertice and then draw in as many diagonals as you can. And it can only have one when it goes out of that one vertice, creating two triangles. So 180 here, 180 here. So 180 plus 180 is equal to 360. This is how they're coming up with the formula that I'm gonna show you on the next slide. So to find the sum of the interior angles of a polygon, we're going to be using this formula that's over here. It's n minus 2 times 180, where n in the formula equals the number of sides in your polygon. So for example, in the case of the triangle, we already learned the triangle sum theorem, which told us that the three angles of a triangle add up to be 180. But I could also still use this formula for the triangle if you ever forget. So remember, your n value when it's a triangle will be 3. And if you use the formula 3 minus 2 times 180, 3 minus 2 is 1 times 180, and that will give you the sum of the three angles of the triangle. But again, but I guess by this point, you should already know that the three angles of a triangle add up to be 180. But if you ever forget, then you just use the formula. It works for any polygon, and the formula is the same. It's always minus 2 from the number of sides, and then you multiply it by 180. This will give you what all the angles in the quadrilateral or triangle or pentagon add up to be. So let's take an example of the pentagon. So a pentagon, you should memorize that it has 5 sides. So if I plug it into the formula, n minus 2 times 180, 5 minus 2 times 180, you're going to multiply 3 times 180, and that sum of all 5 angles will be 540 degrees. Okay, so you're going to memorize n minus 2 times 180, and on the next slide, it's actually presented as a theorem. So the polygon interior angles theorem just states that the sum of the measures of the interior angles of a convex polygon is going to be n minus 2 times 180. This gives you the sum. And a corollary to that theorem states that the sum of the measures of the interior angles of a quadrilateral is 360. So really, it's just using that formula and plugging in a 4 for your n. So just like we learned the triangle sum theorem, that the sum of the angles in a triangle are 180, now they're giving us a corollary for the quadrilateral. And all quadrilaterals, whether it's a square, a rectangle, or a rhombus, will always add up to be 360. It doesn't matter, as long as it has 4 sides, the sum will always be 360. Okay, the next slide has 3 vocabulary words. And we've seen the first 2. The word equilateral means all sides congruent. And we learned to name triangles as an equilateral triangle, and that told us that all the sides in the triangle were congruent. Now this term applies to any polygon. So when you have a picture, and if you see congruency marks on all the sides of the polygon, if they all have the same congruency mark, then you can say the polygon is equilateral. If they all have congruent angles, then you could name the polygon as being equiangular. And then when you see the word regular in front of one of the polygon names, that means that all sides and angles are congruent. So in other words, it's both equilateral and equiangular. So for example, we're going to be seeing this term, the term regular, quite often. And the way that it'll be used is you're going to write down the word regular, and then they'll write one of the polygon names. So let's say they put the word regular pentagon. Soon as you see the word regular in front of a polygon name, that tells you that all the angles and all the sides in that particular polygon are going to be congruent. Okay, so for the first one, it wants me to classify the polygon by the number of sides and then decide, is it equilateral, equiangular, or regular? So let's go ahead and take a look at A. I'm going to count my sides. I have 1, 2, 3, 4, 5, 6 sides here. So this is a hexagon. And now I'm going to go back and look to see if the sides are the same and if the angles are the same. Notice all 6 sides have the same congruency mark, making all sides congruent. So when all sides are congruent, this is called equilateral. And now if you go back and look, also all 6 angles are congruent. So when all angles are congruent, then it's called equiangular. And when it's both of these, then we could actually just say that this hexagon is regular because it has both all sides congruent and all angles. So because it's both equiangular and equilateral, this is a regular hexagon. Next, I'll look at the picture in B. I'm going to count my sides. It has 1, 2, 3, 4 sides, making this figure a quadrilateral. And now I'm going to go back to look at the sides. Notice all 4 sides, they have different markings. So I do not have all sides congruent. And the same thing with the angles. So this is just a quadrilateral. It's not regular, it's not equiangular, and it's not equilateral. It's just a quadrilateral. Coming up after Thanksgiving, we're going to learn that this is a parallelogram. And then C, let's go ahead and count how many sides this one has. So this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 sides, making this figure a dodecagon. 12 sides. Now, I'm going to go back now and look at the congruency marks. Notice all 12 sides have the same mark. So this would make this, all the sides are equal, are congruent, making this equilateral. However, not all 12 angles are the same. Notice here, I've got a little right angle here, 2, 3, 4, 5, 6, 7, oh, not that one, 7, 8. Only 8 of them are right angles, and then these are not congruent, so it's not equiangular. So it's just an equilateral dodecagon. This is a concave polygon, so really we can't apply the word regular to it because we're not going to have all 12 angles congruent. So you see this angle here is not congruent to the right angles. Okay, the next one is a theorem, and it's called the polygon exterior angles theorem. And this theorem states that the sum of the measures of the exterior angles of a convex polygon, one angle at each vertex, is 360. So it doesn't matter what kind of polygon I have, the exterior angles will always add up to be 360. It doesn't matter if it's a hexagon, the sum of the exterior angles is 360. It doesn't matter if it's 100-agon, it'll be 360. So if I ask you a question on the quiz and I say, what is the sum of the measures of a decagon of the exterior angles of a decagon? You're going to tell me it's 360. Okay, this is only the sum of the exterior. To find the sum of the interior, you have to use the formula. So it doesn't matter what the polygon is. So let's say we have a regular triangle, and I'm going to extend the sides to create exterior angles. So if I extend it this way, and let's say I extend it this way. So this is creating, and let's say this is a regular triangle. So remember, regular means equilateral and equiangular. How much is each angle in an equiangular triangle? 60. Good. We learned that corollary. So each of these are 60. If you forget, you just take 180 and divide it by 3. So if I tell you that this is a regular triangle, then you know that all angles are the same and all sides are the same. Now, notice the interior and the exterior angle. Notice they're forming a linear pair right here. So to find the exterior angle, I could just do 180 minus 60 in this case and get 120. And then this one would be 120, and so would this one. And these would be the three exterior angles of this regular triangle. And if I go back and add 120 plus 120 plus 120, notice my sum, 360. So the exterior angles of any polygon will always add up to be 360. In this particular example here, all of these red numbers, these are all the exterior angles of this polygon. And it's a pentagon. It's not regular, but it's a pentagon. And it doesn't matter if it's regular or not, all the angles on the outside, the exterior angles, will always add up to be 360. Now, the formula we saw before, the n minus 2 times 180, remember that gave us the sum. Now we're going to take that formula and manipulate it, and now all we have to do is divide that formula by n, and that'll give us the measure of each individual interior angle in a regular polygon. So let's just do the same thing that I did before the triangle. So let's say we have a regular triangle. We're going to use our formula, n minus 2 times 180, and we're going to divide it by n. Remember, in a triangle, 3 sides, so my n value is 3. So 3 minus 2 times 180 divided by 3. 3 minus 2 is 1. 1 times 180 divided by 3. So 180 divided by 3. And that's how we get what each angle in our interior angle of our regular triangle equals. It works for any regular polygon. You're going to need to be able to use these formulas, be able to find each, be able to work backwards if I give you the measure of each, and find the number of sides. And I'm going to add one more example to the notes demonstrating this, because it will be on the test. So when I add the example, make sure you're paying attention. Do some examples. Notice it has 2 parts. It wants me to find the sum. Now, when you're taking this test, you have to watch the wording. If it asks for sum, then all I'm using is the n minus 2 times 180. If it would have said each, then I divide it by n. But it wants sum, so I'm just using that formula. For my part B, what are the exterior angles always sum to be or add up to be? 360. So for both of these, my answer for B is 360. But let's do the part A. So how many sides are in a heptagon? 7. So my n value is 7. So I'm going to do 7 minus 2 times 180. I get 5 times 180, and that gives me 900. So when you're doing your homework, even though you're using your calculator, this is what I want to see, how you know how to use the formula. You don't have to show me the 180 times 5 because I know you're using your calculator. But show me that that is what you're putting in your calculator. And show me the 5 times 180 in your work. So that's for part A. Part B, we already said, the sum of the exterior angles is always 360. The next one is a 17agon. So this tells me my n value is 17. 17 minus 2 times 180. This gives me 15 times 180, which gives me 2,700. And these are degrees. Make sure you're including the degree symbol. Part B, doesn't matter what type of polygon it is, the sum of the exterior will always be 360. Okay, example 3. This time it wants us to find the number of sides, so we're looking to solve for n of a convex polygon that has a sum of the interior angles to be 900. So I'm using the formula n minus 2 times 180, but I'm going to set that equal to the sum that they gave me. I'm going to solve this 2 ways. I'm going to first do it by distributing, and then I'm going to also show you another algebraic way to do this. So the first way would be to distribute the 180 to the n and to the 2. So 180n minus 360 equals 900. I'm going to add 360. I get 180n is equal to 1,260. Divide by 180. And the number of sides in this polygon is 7. Now, if it asked us to name it, we would say that this is a heptagon. But if all it asks you to list or tell is the number of sides, you say 7 sides. Now, the other way you could solve this, and it depends on how your Algebra 1 teacher taught you, you can also solve it this way. So n minus 2 times 180 equals 900. Anytime I have something that I'm supposed to distribute into a parenthesis, instead of distributing, I could divide both sides by 180 to begin with. I'm going to do this in a darker color. I'm going to divide by 180. That cancels the 180, and now I'm just left with n minus 2, and then 900 divided by 180 is 5, and then add 2 to both sides, and you get n equals 7. So you can choose either method for solving for the side length. And again, when you get questions like this, I want to see how you're solving it algebraically. Okay, next slide. Now they want us to find each interior angle and each exterior angle. So for each interior, remember this formula is n minus 2 times 180 and then divided by n. That gives us each interior. For each exterior, remember the sum is 360. So for that, you just take 360 and divide it by the number of sides. So you divide it by n. So let's go ahead and do each one. So for the regular quadrilateral, I'm going to take 4 minus 2 times 180 and then divide it by 4. 4 minus 2 is 2. 2 times 180 divided by 4. 2 times 180 is 360 divided by 4, and I get 90. This is the interior angle of a regular quadrilateral. In other words, a square. When we want to do the exterior angle, I'm going to do 360 divided by the number of sides. Notice it's the same calculation I just did, and it's 90. Remember, the interior plus the exterior, when you add them, remember, they're supplements. So when you add these two, you should be getting 180. If you don't, you've done something wrong. Technically, what you could do is once you find the inside, the interior angle, you could just subtract it from 180, or vice versa for the exterior. Let's try the octagon. 8 sides. This is where you need to know that your n value is 8. So 8 minus 2 times 180 divided by 8. This gives me 6 times 180 divided by 8. 6 times 180 is 1,080 divided by 8, and I get 135. And now for the exterior angle, you could either right now subtract 180 minus 35 or do the appropriate calculation of 360 divided by 8. And that will give you 45 degrees for the exterior angle. And remember, if you go back and add 135 plus 45 needs to equal 180 or you've done something wrong. For the 15agon, your n value is 15. 15 minus 2, it's always minus 2, times 180. And then divide by the number of sides, which is 15. So 15 minus 2 is 13. 13 times 180 divided by 15 gives me 2,340 divided by 15, and the interior angle is 156 degrees. My exterior angle, I take 360, divide it by 15, and that gives me 24 degrees. And again, you can check it by adding the 156 plus the 24. If you're not getting 180, you've done something wrong. Go ahead and add a page. I'm going to do one more example. Pay close attention because this will come back. Okay, so here is the question. It's going to say, find the number of sides in a regular polygon given that each angle equals 165.6 degrees. So the formula we're going to use is n minus 2 times 180 divided by n, and this is going to give us what each angle equals. And they gave me what each angle was, 165.6. So let me go ahead and fill it in. This is where your algebra skills come in. So n minus 2 times 180 divided by n equals 165.6. This is what will be given to you. The first thing you're going to do to solve this algebraically is to get rid of the fraction. So I'm going to multiply both sides by n. It cancels the fraction. Next, I have to distribute. So I'm going to distribute the 180. This one I can't divide by 180. I have to distribute. So 180n minus 360 is equal to 165.6n. I now need to get my n's together. So I'm going to subtract the 180. So 100 minus 180n from both sides. And now I get negative 360 is equal to negative 14.4n. And now divide. Negative 14.4 on both sides. And n equals 25. So this would be a 25-agon.